1949, a mathematician sits down and solves Einstein's equations, not to find black holes, not to predict gravitational waves. He was simply preparing a birthday gift for his closest friend, and he found a universe where time does not exist, not metaphorically, not philosophically. In the strict, unforgiving language of pure mathematics, a valid solution sitting right inside the very equations Einstein had spent his entire life building. In that universe, causality is no longer a law. The past is no longer something that has passed. And you, if you travel far enough in exactly the right direction, can loop back and meet yourself before you ever took the first step. Here's what makes this genuinely unsettling. Not that the solution is strange. What makes it unsettling is that it is completely legitimate. No exotic matter, no impossible ingredients, no violations of any rule Einstein ever wrote down. If this is real, not as speculation, but as a true mathematical possibility embedded in our best theory of reality, then everything we think we understand about time, about cause and effect, about the arrow of the universe is standing on ground far thinner than we ever imagined. Subscribe to join us as we bend reality. Now let us begin. The man who found this was not a physicist. That is not a minor detail. That is the entire point. Kurt Gödel was a logician, a mathematician of the purest kind, someone who spent his life not measuring the physical world, but interrogating the foundations of thought itself. In 1931, he had already done the impossible once. His incompleteness theorem shattered a century of mathematical ambition by proving that every formal system contains true statements that cannot be proved within that system. Mathematics, the language we trusted most, had a ceiling it could never break through from the inside. So when Gödel turned his attention to Einstein's general relativity, he brought no physical intuition with him, no preconceptions about what a universe should look like, no instinct whispering that certain solutions were too strange to take seriously. He read the field equations the way a master locksmith reads a mechanism, not asking what it was built for, but asking what it could actually do. The occasion was Einstein's 70th birthday. A group of colleagues were assembling a tribute volume, and Gödel agreed to contribute an essay. His original intention was modest, a philosophical reflection on the relationship between Einsteinian spacetime and the ideas of Immanuel Kant. Then he fell down the rabbit hole. The deadline passed. The entire volume had to wait, because what Gödel had stumbled into was not a philosophical footnote. It was a fault line running directly through the core of his best friend's greatest theory. Think of Einstein's field equations as the architectural blueprints of the universe. Every solution to those equations is a valid universe, a different possible shape that reality could take. Einstein drew the building. What Gödel found was a room Einstein never knew existed. And inside that room, time ran in circles. Before we can understand what Gödel found, we need to understand what he was working with, because the strange effect only becomes visible once you see the architecture it is hiding inside. Einstein's general relativity tells us something deeply counterintuitive. Space and time are not separate stages on which the universe performs. They are woven together into a single four-dimensional fabric called space-time, and that fabric is not rigid. Mass bends it, motion stretches it. Gravity is not a force pulling you downward. It is the shape of space-time itself, curving underneath you. To visualize this, physicists use something called a light cone. Imagine you are standing at a single point in space-time, right here, right now. From that point, light races outward in every direction. The boundary traced by that expanding sphere of light forms a cone when you draw it against the dimension of time. Everything inside your forward light cone is your reachable future. Everything inside your backward light cone is the past that could have influenced you. Everything outside those cones is permanently unreachable. No signal, no force, no information can connect you to those regions without exceeding the speed of light. This is not merely a speed limit. It is the architecture of causality itself. The reason your past cannot be rewritten and your future cannot be visited is precisely because your light cone keeps those regions sealed off. Now introduce gravity. A massive object bends space-time, and that bending tilts your light cone. Near a black hole, the curvature becomes so extreme that your entire forward light cone rotates toward the event horizon. Below that horizon, the light cone tips completely sideways. The direction we once called downward becomes your new time coordinate. You cannot turn around. You cannot escape. Your entire future points in one direction only. In a rotating black hole, what physicists call a Kerr black hole, something even stranger happens deep within. The rotation of the black hole drags space-time around with it like a spoon stirring honey. This effect is called frame dragging. And in certain regions deep inside a Kerr black hole, this dragging becomes so powerful that a circular path through space becomes a path through time. You could travel in a loop and arrive back before you left. Physicists call these closed time-like curves. But here is the problem. Every known mechanism for producing closed time-like curves requires something deeply problematic: negative energy density, a quantity that may not exist in any physically meaningful sense. So physicists added a rule, the weak energy condition, a constraint that simply forbids negative energy, and with it forbids all of these troubling solutions. For a while, that rule seemed like a perfect lock on the door. Gödel found a key that did not need to pick it. Gödel did not add anything exotic to Einstein's equations. He did not smuggle in negative energy or hypothetical matter or physics that had never been observed. He made one quiet, seemingly innocent change to the assumptions underlying the solution. He let the universe rotate, not a single object rotating inside the universe itself, every point in space-time carrying a fundamental twist relative to every neighboring point. No center, no axis, just a global, all-pervading rotation woven into the very fabric of existence. Physicists call this property global vorticity, and it sounds abstract until you understand the mechanism that makes it dangerous. That mechanism is frame dragging. You have almost certainly never felt frame dragging in your daily life, but it is real and it has been measured. In 2004, NASA launched Gravity Probe B, a spacecraft carrying 4 of the most perfectly spherical gyroscopes ever manufactured. A gyroscope, under ideal conditions, always points in the same direction. It is what Gödel himself called an inertial compass. But as Gravity Probe B orbited Earth, those gyroscopes slowly drifted, not because of any mechanical imperfection, because Earth's rotation was dragging space-time around with it, and the gyroscopes had no choice but to follow. Earth's frame dragging is extraordinarily weak. You would need to orbit the planet an almost incomprehensible number of times before the accumulated time shift became meaningful. But Gödel realized something that no one had fully confronted before. If frame dragging exists everywhere, if global vorticity is baked into the structure of space-time itself rather than localized around a single spinning object, then the effect does not stay weak. It accumulates. It compounds. And at a sufficient distance from any starting point, it accumulates enough to do something that should be impossible. It tilts the light cone all the way back toward the past. Here is how the Gödel universe is structured. The geometry is hyperbolic, shaped like an infinite saddle surface with negative curvature that allows centerless rotation without any contradiction. Matter is distributed smoothly and uniformly throughout. A carefully tuned cosmological constant keeps the universe static in size. And the global vorticity threads through every point in space-time like an invisible current running through still water. From any point in this universe, as you travel outward, your light cone tilts, gradually at first, then more severely. Beyond a critical distance, what we can call the Gödel horizon, the tilt has accumulated enough that your forward light cone now contains points in your own past. A carefully planned loop through space, extending beyond that horizon, becomes a path that deposits you back before you departed. No negative energy required, no exotic matter, no violation of a single line Einstein ever wrote. And this is precisely what made it so deeply unsettling. Every solution to Einstein's field equations that allowed time travel before Gödel had required some ingredient that physicists could reasonably dismiss as unphysical. The weak energy condition was the rule that swept them all away. But the Gödel universe satisfies the weak energy condition. It uses only ordinary matter and a cosmological constant, a term Einstein himself had already introduced and later removed from his equations. There is nothing in Gödel's solution that Einstein's own theory can reject. The result is a valid universe in which closed time-like curves do not merely exist in some remote, inaccessible region. They are everywhere. They are structural. Time travel in the Gödel universe is not an exotic edge case. It is a fundamental feature of the geometry. And with that, the question that physicists thought they had safely locked away came back through the door it was never supposed to use. If a universe like this is mathematically legitimate, if Einstein's equations permit it without complaint, then what exactly is it that prevents our universe from being one? Let us pull this down from the level of equations and horizons and four-dimensional geometry. Let us make this uncomfortably personal. Right now, as you are watching this, your body is made of approximately 7 billion atoms. Every single one of those atoms exists inside space-time. Not near space-time, not affected by space-time from a distance, inside it, woven into it. subject to every rule it operates by. If the universe carries even a residual global vorticity, even a rotation so slow and so subtle that no instrument we have built has yet detected it, then every one of those atoms is being dragged along a curve that does not run straight through time. It spirals imperceptibly, immeasurably, but structurally. The ground beneath your existence is not flat. It never was. Now consider what that means for something you have always taken for granted. Causality, the assumption that what you did 5 minutes ago is the reason something is happening now. The assumption that your decisions move forward into a future that has not yet been written. In a universe with closed time-like curves woven into its geometry, that assumption becomes a question rather than a foundation. Not because anyone has proved it false, but because Gödel demonstrated with complete mathematical rigor that Einstein's equations do not guarantee it is true. You are not just a person watching a video about an abstract solution to a physics equation. You are a collection of matter that exists inside a space-time whose complete rulebook has not yet been written. The physicists are still working on it. The telescopes are still gathering data. And the equations, the same equations that predicted black holes, gravitational waves, and the bending of light, are still quietly containing rooms that no one has fully mapped. What else is hiding in there? That question has no comfortable answer. And it was never supposed to. To be fair, most physicists do not lose sleep over the Gödel universe, and their reasons are legitimate. Let us take those reasons seriously before we examine what they leave unresolved. The most immediate objection is observational. The Gödel universe does not expand. It is static, frozen in size, held in place by a precise balance between matter density and a cosmological constant. But our universe is expanding. Edwin Hubble established that in 1929, and every precision measurement since has confirmed it. A rotating static universe simply does not match what we observe when we point our telescopes at the sky. The second objection is structural. The Gödel solution requires a negative cosmological constant to maintain its static geometry. Current observations suggest our cosmological constant is positive, the same term responsible for the accelerating expansion we associate with dark energy. The numbers do not match. So the standard dismissal goes something like this. The Gödel universe is a mathematically valid but physically irrelevant curiosity. An interesting exercise. A reminder that the equations are richer than any single solution. Nothing more. Here is where that dismissal becomes uncomfortable. We have heard this kind of confidence before. Einstein himself looked at the equations of quantum mechanics and declared that God does not play dice. He was wrong. The universe played dice anyway, and it did not ask for his approval. Scientific history is not a record of theories being confirmed. It is largely a record of assumptions being revised by data that nobody expected. And right now, the data is becoming inconvenient for our standard assumptions. The Hubble tension is real. Two independent methods of measuring the expansion rate of the universe, one looking at the cosmic microwave background from the early universe, one tracking supernovae in the modern universe, consistently disagree with each other by an amount that has only grown more statistically significant as measurements have improved. As of the most recent analyses in 2024, the discrepancy sits at a level that is extraordinarily unlikely to be random noise. In 2025, the dark energy spectroscopic instrument reported strong indications that dark energy is not constant, that it has weakened over cosmic time. Lambda CDM, the standard model of cosmology that has dominated for decades, is showing cracks. None of this proves Gödel right. That would be a leap far beyond what the evidence supports. But it demonstrates something important. The model we use to dismiss Gödel's universe as irrelevant is itself under pressure. The universe does not care how elegant our assumptions are. It only behaves according to its own rules. And we are still learning what those rules actually say. So where does this leave us, and where are we going? The good news is that we are not simply waiting in the dark. Within the next decade, several instruments will come online that are capable of probing precisely the kinds of questions that Gödel's solution forces us to ask. And the results, whatever they turn out to be, will matter enormously. The Einstein telescope is a next-generation gravitational wave observatory currently being developed in Europe, with operations expected sometime in the early 2030s. It will be approximately 10 times more sensitive than LIGO. That sensitivity matters here because gravitational waves carry imprints of the space-time geometry they travel through. If our universe carries any residual global vorticity, any structural rotation at the cosmological level, that signature may appear as a subtle but systematic anomaly in the polarization patterns of gravitational waves arriving from different directions. The Einstein telescope may be capable of detecting or ruling out effects at that scale. CMBS-4 is a next-generation cosmic microwave background experiment scheduled to begin observations in the late 2020s. The cosmic microwave background is the oldest light in the universe, a snapshot of conditions approximately 380,000 years after the Big Bang. If the universe were rotating at the time that light was released, we would expect to find a specific pattern of asymmetry in that light. CMBS-4 will map the microwave background with a resolution and sensitivity that dwarfs anything we have achieved before. If that pattern exists at any detectable level, CMBS-4 will find it. The Vera Rubin Observatory is already beginning its legacy survey of space and time, a 10-year program that will map approximately 20 billion galaxies across the southern sky. If the large-scale distribution of those galaxies carries a systematic spiral pattern that cannot be explained by known physics, it would represent a potential signature of global vorticity embedded in the structure of the universe itself. None of these instruments was designed specifically to test Gödel's solution, but that is often how the most important discoveries arrive, not through experiments designed to find a specific answer, but through precision measurements sensitive enough to reveal structure that our current models did not predict. And that brings us back to the room that Gödel found inside Einstein's equations. He was not trying to break general relativity. He was trying to give his closest friend a birthday gift, a mathematical reflection on the nature of time. What he produced instead was a demonstration that the greatest theory of reality ever constructed was not yet complete. That somewhere inside its own mathematics, it permitted universes that its author had never imagined and could not easily explain away. Gödel did not crack the foundation. He found the places where the foundation had not yet been poured. Every generation of physicists since has worked to fill those gaps with new conditions, new conjectures, new observational constraints. Hawking proposed that any space-time permitting closed time-like curves would destroy itself through quantum feedback. Penrose proposed global hyperbolicity as a requirement that physically reasonable spacetimes must satisfy. Both proposals are serious. Neither has been proved from first principles. The work continues. And here is the thought that stays with me at the end of all of this. Gödel sat down to honor a friend and accidentally proved that time, as his friend had described it, was more fragile than either of them knew. He handed Einstein not a tribute, but a challenge. Not an answer, but a deeper question. That is what the best science does. It does not close doors. It reveals that the hallway is longer than you thought, and that some of the doors you were certain led nowhere are still worth opening. We do not know whether our universe is rotating. We do not know whether closed time-like curves exist anywhere in the accessible cosmos. We do not know how many other valid solutions to Einstein's equations are sitting undiscovered, waiting for someone who is not a physicist to read the blueprints without any preconceptions and find another room nobody knew was there. What we do know is this. The equations are still speaking. We are still learning how to listen. And the strangest effects, as Gödel showed us, appear precisely when you solve them in the way nobody thought to try.